Hello, I'm Romain Cosson, and this is joint work with Laurent Massoulie at Inria. This talk is about collective tree exploration, which models the exploration of unknown environments with multiple mobile agents. And the technique we used is the potential function method that is inspired from the world of online algorithms. The main question of this talk is whether maze solving is parallelizable. To put it in very simple terms, imagine you're lost with a bunch of friends in a maze. Can you find the exit faster than if you were on your own? So the model that we take is extremely simple. It is that the maze is a tree. It's a tree with n nodes, so n is also roughly the number of edges, and depth d. Now, maze solving is a problem that dates back to the antiquity. It appears in the Greek mythology, but also it also appears in modern applications, such as search of game trees or Monte Carlo tree search. Now, if there is one agent in a maze or in a tree, one way to explore it is to put their right hand on the wall and to go forward. By doing this, the agent effectively implements depth-first search, so it is guaranteed to go through all edges twice, once in each direction, and then to go back to the origin. So it will find the exit in at most 2n moves. If there are two agents in a maze, there is one way to parallelize this procedure. Have one agent put their right hand on the wall and the other agent put their left hand on the wall. By doing this, they will meet after just n time steps, and when they meet, well, they have a full map of the maze and they can go right to the exit by using the shortest path. So this procedure is completely distributed, and notice that the agents don't even have to communicate until they meet. So it looks like maze solving is completely parallelizable for k equals 2. But unfortunately, parallelization becomes much harder as soon as k equals 3. Now, in this problem, I'll be talking about exploration than maze solving or search. The reason is that from the point of view of worst case complexity, these two problems are completely equivalent. This is because an adversary could put the exit of the maze at the last visited edge. The goal, in fact, of collective tree exploration is to explore all edges at least once. So this is precisely the setting that was introduced by Fregno, Gazieniec, Kowalski, and Pelk in 2004 in their paper Collective Tree Exploration. They assume that there is an unknown tree, T, with n nodes and depth d, and that there are k agents moving synchronously at each round. Now, in this model, the agents also have to all return to the origin. That makes calculations a little simpler, though it doesn't change the nature of the problem. They introduced two communication models. In the first communication model, the agents can communicate at all times and at no cost. It is like if they had cell phones, or if there was a ground control which was in charge of capturing the entire information that is known about the maze and then broadcasting it to all the agents. In other, more difficult communication models, the agents can only go in the maze with one clay, and they read and write information at whiteboards with unbounded memory that are located at all nodes. The main result of these authors is that they provide an extremely simple algorithm, split, that perhaps is the simplest algorithm you could think of. It's just like when a group of agents arrives at an intersection, it splits into two teams of same size. So the algorithm is called split. And they provide for an analysis for this algorithm in 2n divided by log k plus d. So in some sense, they achieve a parallelization with k agents in log k. Notice that the algorithm split is distributed. It can be implemented with just the clay, where in the setting where the agents just navigate with the clay. But also notice that although it only provides a logarithmic improvement over depth-first search, it was not improved for a long time. So where does this log k comes from in split? Just to explain where it comes from, I'm going to take this very simple example of a tree that we call the comb, because it looks like a comb. In this tree, which is a triangle also, it has n equals d squared number of nodes, roughly, because it's a triangle. And assuming you have 4 agents for the sake of the illustrations that all start from the root, at the first round, the first thing that the agents are going to do is that they're going to split into 2 groups of same size. Now at the next round, the left group is going to split again, and the right group is not going to split until it reaches the bottom of the tree. After a few rounds, all the groups are in different branches, and they will eventually reach the bottom of the tree in D moves. And then, synchronously, they move back up to the root, not to the root, to a deeper node, and maybe they will start again another round of exploration from here. As you have noticed, the agents, if there were k agents, the agent will have explored log of k branches. So you need d divided by log k such steps, because they are d branches. Now each steps take d times steps. So roughly, this procedure of exploring the comb takes d squared divided by log 2k rounds. So that's actually omega of n divided by log 2k. So this explains what the split procedure requires at least n divided by log 2k. It doesn't provide more than the logarithmic speedup. And actually this lower bound not only works for this algorithm, but for any greedy algorithm. This was noticed by Higashikawa and co-authors, and they define a greedy algorithm by saying that it is an algorithm where a robot never leaves a subtree that is unfinished. It has to participate to finishing the subtree at the top of which it is located. So let's try to make a little bit more formal the definitions. And to do this, I'll introduce another problem that is tightly connected, that is called the offline variant of collective tree exploration. Denote by OPT, opt, the exploration time that is required for all robots to go through all edges and meet at the origin if the tree were known in advance. This time is at least 2D, because obviously the robots have to go from the root to the deepest node and then back to the root. This time is also at least 2n divided by k, because at each round, at most k edges are explored, and all edges must be explored once in each direction, since the robots must meet at the root again. This means that opt is greater than the average of those 2 quantities, and actually this is the right order of magnitude. Opt is roughly equal to this quantity. With this lower bound in mind, we actually have immediately that split has a competitive ratio in k divided by log k, because the quantity on the left is obviously bounded by k divided log k times opt. And from the example we saw at the slide just before, any greedy algorithm will actually achieve the same competitive ratio. So this talk is actually precisely focused on this quantity, which is a quantity that is central in online algorithm, which it is about pushing down the competitive ratio to big O of square root k. Now, in parallel to the competitive ratio approach, a regret approach or competitive overhead approach was developed by Brass, Mora, Gaspari, and Xiao in their paper Multi-Robot Exploration, starting in 2014. They proposed an analysis of split, so this distributed algorithm, in 2n divided by k plus d to the k. So obviously, the d to the k term here is much bigger than before, but observe that for very small values on d, on very large values of n, so in some sense for very dense trees, this runtime is actually better than the runtime that was analyzed by Fregno and co-authors. With Laurent Massoulie and Laurent Vienno, we improved this regret guarantee to log k times d squared, and then I recently presented an improvement of the d squared term to a linear in d dependency, but at the cost of a much higher dependency in k that is super polynomial. This talk is about also a regret term that is in big O of kd, so it's linear both in the number of robots and in the depth. The reason why studying the regret is so interesting is that linear in D regret actually has a tight connection to the competitive ratio. So this table summarizes the results that are on the left. Initially, what was known in 2004 was a competitive ratio of k divided by log k. Then came the first regret analysis of d to the k, which was improved to log k times d squared, and then to the super polynomial in k times d. But these recent linear in D regret guarantee actually provide a better competitive ratio, and this talk is also about a square root k competitive ratio. So let me explain why a regret in KD implies a competitive ratio of square root k. The proof is actually extremely simple, so I'm going to do it. Assume that you have an algorithm that runs in 2n divided by k plus kd. Now consider another algorithm that actually uses only a fraction of the robots, k prime, of square root k. Then the runtime of this algorithm is bounded by 2n divided by square root k plus square root kd. Now if you factor out square root k, you obtain the competitive ratio of in big O of square root k. So this is actually kind of counterintuitive, because the algorithm that is the most competitive, we know, doesn't use all the robots, or more precisely, it only uses a very small fraction, square root k fraction of the robot. Now let me say a few words about the techniques that we use, and particularly the tree mining game. The first thing is that we consider asynchronous collective tree exploration, which is a generalization of collective tree exploration. In this setting, the adversary controls at all times the speed of each of the robots, and the player pays for the total distance that was traveled by the team collectively. So the adversary could choose to break down a robot indefinitely, so now the robots are not required anymore to go all back to the root. Notice that this setting remains much harder than collective tree exploration, which is a synchronous setting in which the adversary is forced to move all robots at the same time. To illustrate this, let me just go back to the example of split. At the first round, maybe the adversary is going to let all robots move by one step, but maybe at the next round, it will only move the two robots on the right. And by doing this, in a sequence of iteration, only the first branch of this very specific tree that we call the comb will be explored. So it is actually very easy to show that the split algorithm will take omega of n steps irrespective of the number of robots. So there will be no speed up in this asynchronous setting. The reason why we are interested in asynchronous collective tree exploration is because there is a tight reduction between that setting and a game that is very close in spirit to online algorithms, and that is called the tree mining game. So let me just explain a little bit what the tree mining game is about. In the tree mining game, there is a player, there is an adversary, and there is a board. The board is actually a mine that is a tree that's different from the tree that is explored by the robots. And this tree is a very natural tree with a set of vertices, a set of edges, and a set of leaves that we call active leaves. And it has, every active leaf has a number XL associated to it, which corresponds to the number of miners that are mining at this leaf. In the example on the right, there are 2 miners on the active leaf of the left, and 1 miner on the active leaf of the right. And at each round, the adversary is going to choose one of the active leaf and provide it with XL minus 1 children. So for instance, if it chooses the active leaf on the left, it provides it with 1 children. And if it chooses the active leaf of the right, it provides it with 0 children. Then the player has to relocate the miners so that they are located on an active leaf. So we define a FKD bounded strategy as a strategy in which the miners are guaranteed to reach a certain depth d in at most FKD moves. And finding such a strategy actually gives you a FKD divided by k regret for collective tree exploration. In an example of a move in this game here will be that the adversary will choose a node with 2 robots here and provide it with 2 minus 1 children, and that the player would relocate both robots to that newly created leaf at a cost of 2. The way we analyze the tree mining game is by the potential function method. So we defined the potential function on a tree of a configuration x by the sum over u, the set of nodes, of phi of xu, where xu is the number of minors below node u. So in this simple example, this potential function method appears in a lot of other problems in online algorithms and in very recent developments on the K-server problem and on metrical task systems. But it was never used in collective tree exploration. As a very simple example, consider the quadratic function phi of x equals x squared. For this function, if you assume that the left, if you take d1 to be equal to 2 and d2 to be equal to 3, because there are 2 nodes on the left branch and 3 nodes on the right branch, you get the following potential, d1 x1 squared plus d2 x2 squared. And the algorithm that we propose actually tracks the optimal configuration for this potential. Notice that in this case, this corresponds to the electrical current that will flow on both branches if you impose an inwards electrical current of 1 at the root and an outwards collective current of 1 at the leaves. And there is kind of a natural interpretation that's very nice to this, is that if X is the electric current in a network, there is perhaps a reason that we can connect to the way electrons have actually short-range interactions that are repulsive and are therefore quite good explorers, quite good at exploring, at spreading in a network. In the analysis of any potential function method, you have an equation that looks roughly like this, where you can bound the algorithm's cost by some big potential that evolves continuously with the tree, which is here the electric loss of the network if the tree was known in advance. And the potential also appears on the left to counterweight the moments where the cost is going to increase a lot. And this equation is used at the ultimate time step, Tf, to obtain a guarantee in gamma times, in a constant times t squared times k squared times d. And then our reduction actually implies the 2n divided by k plus big O of kt exploration algorithm. I encourage you again to have a look at the paper if you want more details on all of this. So I'll leave you with a few open questions that I believe are interesting. The first is actually not about tree, but about graphs. It is unknown whether there exists collective graph exploration algorithms that are competitive, either in the sense of competitive ratio or in the sense of a regret. The reason why it's difficult to obtain competitive algorithm for graphs is that d here represents the graph diameter. And the diameter of a graph can shrink a lot by just adding a few edges. So obviously, these edges are going to provide shortcuts that will help you explore the graph faster, but it will also make it harder to compete with the optimal solution. That is the difficulty of collective graph exploration. Another important open question is whether there exists a competitive gap between two settings that I introduced, which are synchronous collective tree exploration and asynchronous collective tree exploration. Our methods presented in this talk work for both settings, but it could be the case that we didn't exploit synchrony and the competitive ratio could be improved in that setting. Another setting, two different settings that I also introduced are the distributed setting and the centralized setting. This talk focused on the centralized setting of collective tree exploration, and it is unknown whether there is a competitive gap, again, either in terms of regret or of competitive ratio between those two very natural settings. Thank you very much for attention, and have a look at the paper.